Hello, everyone, and I'm Yuanli Bai, Associate Professor in the MAE department. Today, I'm going to give a talk on mechanics of the biological materials, including soft tissues in virus. And I give a talk 2 years ago in this seminar. Michael invited me, and he invited me again this year. And last time I give a talk on the research on the hard materials, engineering materials, lightweight alloys, and so on. And today I won't give a talk because I start a new line of research on the mechanics of the soft tissues. And soft tissue is not new, but the mechanics of the virus is the brand new. Okay, so if people don't know about me, is that usually I introduce that. And I usually teach the courses in the traditional mechanical materials and machine design and finite element analysis. So the research on the material modeling, testing, plasticity, this is the one, is my talk last time. And the new research interest is the mechanics of the soft tissues and with the medical simulation application. And also the mechanics of proteins. The virus is also protein. And today I'm going to use example is on the SARS-CoV-2, which is the coronavirus. Okay. So this is still my traditional area research, right? Mechanics of the lightweight alloy, like aluminum, advanced high-strength steels, magnesium, and with application to the automotive industries in the aerospace industries and for energy application and absorb more energy. For example, print this in the microlattice, test it and see the failure modes and so on, and collaborate with the Dr. Wu and Dr. Song in our college. So, but this is not the topic today. My talk today is on the mechanics of soft tissues. And the soft tissues we did that is actually started about 5 years ago. No, more than that, it's 7 years ago. And my lab has a project supported from the Army Research Staff to get the mechanics of synthetic tissues. And the purpose is that the Army Research Staff in Orlando try to find out which kind of material is good for the training purpose. So if you see the pictures on the upper right, it's right. The Army, they try to train their doctors. They go to battlefield, and certainly they cannot using animal tissues or cadavers all the time, right? It's very expensive. So let's see what kind of synthetic tissue has a similar mechanical property as the real one. So that's why they have some synthetic tissues and sent to my lab, and we test it, right? And before that, we also a lot of the about 2 years research already on the tissues. And at that time, I collaborated with Dr. Alan Kassav in my department, and also Professor De Campoli from our College of Medicine. And they sent the artery, the pig artery tissues, and we tested, and it's actually very complicated. Right? This is how I started. And in the past, we also test like steels, aluminums, and so on. But when you go to tissues, first thing difficult is that data is not that repeatable. You're going to have, like I said, the error bar is not just 5 or 10%, can 100%, right? And so different samples, quite different, number one. Number two, the deformation is very different. It not to be highly anisotropic. Different orientations is different. So that's why we developed not only uniaxial tension, you can see this figure, but also biaxial. So we have a punch device. You can see the punch device created the equibiaxial loading condition. And then we test it. And for the data with the Army, I cannot share it. But we give them the guidelines and how, what kind of material pick is close to for the training purpose. And also this is going to open a new area, how the tissue material break. This is a new area I try to go into, because in the past we did a lot of, let's say, how lightweight alloy break, what kind of material model is suitable for that into the design, right? Car design, airplane design. But now how about tissue break? This is a new area, and I try to go into. Okay, we have been doing that for 5 years for the soft tissues, and which is support for Army Dept. And in the past 2 years, because we know that COVID has impacted almost every aspect, everyone in the whole world. And even today, we already fully reopened. But you look at the impact, how many coronavirus they still accumulate, how many deaths, almost 7 million deaths, right? It's continue. The COVID, this is not the pandemic is not the first time, but certainly it's not the last time. Maybe some year later, right? Something come back. So we're going to do research on that. And 2 years before, everyone was watching which this is the coronavirus, which field, and also we stay at time, stay at home, and we see, hey, can we do something, right? And to understand the mechanical properties of the coronavirus. And you're going to find that in the past 2 years, there's a lot of paper published on high impact journals, like say Nature, Science, Share, and to understand what is the inside, this is the coronavirus. And then, so what's the mechanical property? What's the stiffness? Certainly it's nonlinear, so nonlinear. So we start with the, understand, okay, so molecule structures. So we know this is the alpha helix. You see the particular weak part is this is the spike protein. And if you look inside here, you can see it is the alpha helix. And 3 left hand alpha helix hold on right hand tropocoligons. And so you try to predict what's the properties, right? For example, it's like a spring. You can see the spring here, and then they're going to stretch, have large stretch. And is they going to fatigue, going to be break? So we spend time to, from the, use some, let's say, molecule protein structures published in Share, right, the top journals, and then assumed the stiffness between the carbon-carbon covalent bond, and then predict their mechanical property. So you're going to see that you predict the stiffness is like the hyperelastic properties, and also compare with some molecular dynamic simulation. And later on, we found that even more in details about the whole spike has this model available from UC San Diego. They have analysis support, and they put the model and molecule models available, and pick it and model the beam elements for the carbon to carbon for alpha helix, and simulate it, predict the use the right mechanical properties, and we able to predict the mechanical property. It's very excited. So we published a paper on the biophysical journal. This is the one of top journal in the area. So we push very hard and be able to enter this new area, spend a whole year and a half efforts on that. Okay, so this is the virus part. One part is on the spike protein, and the other part is the virus membrane, the shell, right? The shell part. And we also find a collaborator from Hungary, and they do nano indentation. Right, you can see the nano indentation data and see what's the stiffness. And they also do multiple indentation and see their fatigue. Okay, and then we try to see, understand here, what's the stiffness of this membrane and when they're going to break, right? And they do sharp indentation. And also we collaborate with them. They also try to see the indentation head is not to be sharp, can be flat. Try to have a flat indentation. Because you have one test, usually you cannot get a calibrate, for example, 20 material parameters in highly anisotropic, hyperelastic material models. It's difficult. So we try to with that, and that to be quite interesting. They are the response is very different between the flat head and sharp head. So that's why we still on the way to run a lot of FES simulations and to get what kind of model to consistent model be able to describe the deformation and also the fracture of the virus and the shell or membrane. But actually also it's not empty inside. Inside the shell, you can see there's RNP, there's fluids. It's ended up to be quite complicated. Right, it's much complicated than the engineering materials, honestly speaking. Right? And we spend effort on that and form a team. And because during the COVID, we found that online communication still quite effective through Zoom. So we have a team is from AIDA, not from Germany, and also the Tom was speaking from MIT, and Professor Bruno from Brazil, and the Hungary teams in the Brazil team, they have the access to virus test, the virus. They have the course of medicine. They can handle this wet lab. I try to do some in my lab, but in engineering one, certainly we cannot do so. We have the need to have the cannot handle this kind of wet lab. Right? Maybe in the future, our College of Medicine can find some collaborators. But this is our starting point to understand the mechanical properties of the virus, the spike protein, and also membrane protein. Okay, the purpose is that we see if there's any mechanical way for treatment, cure virus, right? So one is thinking of maybe ultrasound, using ultrasound. Ultrasound is usually used for diagnostic. And the proof the safety range is about 2 to 20 megahertz, 2 megahertz to 20. It's for example, different applications, they use the different frequency. And for treatment, it's already there. For example, kidney stone, right? People can focus the ultrasound and break a kidney stone. So already been there. We are thinking if we can tune the frequency and which can be on the range, resonant frequency of the COVID virus, right? If they can have that and they have large deformation, they can create resonance, large deformation. So that's why we start with try to predict the mechanical property of the stock. They call stock this the alpha helix right here, and then put the geometry. We know the density roughly 1.3, a little bit more than the water, the density of those the violence, and then we predict the frequencies, the first 6 modes, tension modes, right, and torsion mode, bending mode. They do in this range. So we see that hey, maybe you can apply this one to some trial on that. So that's why we started this part of the research. And you can see that another possible failure mode probably is the unwinding. So if you look at the spike head, this is the spike protein head. When you're going to pull it, in the beginning, we assume that maybe just a vibration, but actually you can unwinding because those are large molecules, right? When they deform, probably it's the deformation mode is unwinding, something like that. So this is a new area. It's a lot of exciting, maybe new discovery in the future. So this is it also applications not only on the coronavirus, but of other virus, right? For example, HIV. If you look at the HIV virus, and they are also attached to the host cell through a CD4. So through spike, they attach to the host cell and then go into and then reproduce itself. It's so good, it's only reproduce itself. And so this application in the future, we also go to application like that. And our collaborators already try in Brazil, already try some samples, SARS-CoV-2 volunteer applied the 2 megahertz. Actually, he tried 5 to 10 megahertz frequency and see some damage there already. It's preliminary result. They just published the end of last year. So we are trying to continue on it, and also, but it's so this topic is so challenging, and it's not only just one discipline, mechanics or physics or particular physics. It's chemistry, biomedical, and a lot of areas combined it together. And if you look at it, also cross the multiple scale. If you look at the covalent bond, it's about the size of the atoms, maybe 0.1 nanometer, right? And then go to the spike protein, maybe 10 nanometers. And the coronavirus, 100 nanometers. And all the way to the lung in millimeters and in 100 millimeters. And it's become, if you look at stiffness, it's become soft in soft, right? In the real tissue scale, it's very soft. But if you go to the virus side, it's much stiffer. It's about stiffness is about 20 megapascal. But they become brittle, right? So you can see those twins, and it's a lot of how they're going to deform. What's the deformation mechanism? So this to me is like open a new area. So I'm thinking of maybe in the near term, we already have a lot of preliminary results, paper published and so on, and we're going to try, first try an NSF proposal we're going to try again this year, and also particularly thinking of maybe NIH. NIH, there's a K grant, particularly for the, people not training in the medical science. They try to enter this area. There's a K grant for that. So hopefully, through this platform, we have found some good collaborators from College of the Science in microbiology, chemistry, or maybe College of the medicines. So we can write NIH proposal together. So this is my near term. But long term, I try to open a new line of research. It's not only my traditional area in hard materials, but also go to the soft materials like the tissue and also virus. Okay, so this is the what I have, and of course on the tissue part, we have the one PhD graduate 4 years ago, and also another master is a student working on that, and for the research on the virus is a new area, and hopefully we can have a new student comes, when a new grant comes, and we can set up this is the new line of research. Okay.